Hello, ladies and gentlemen, and thank you for standing by. Welcome to this ASM webinar, Coatings, an Image Analysis Perspective. I'm Joanne Miller, Senior Editor with ASM International, and we're glad you could join us. Today's presentation is part of the ASM webinar series designed to provide information you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. The series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsor of today's webinar is Climax Technologies. Since 1990, Climax has been at the forefront of high-end image analysis, developing solutions for the characterization and analysis of microstructures. In recent years, emphasis has been placed on machine learning algorithms, enabling their customers to go beyond the limits of traditional imaging methods. Climax specializes in the integration of advanced computer vision, building out tailor-made software-hardware solutions that best suit their clients' needs. They exclusively use leading brands of microscopes, stages, and cameras in order to uphold their unwavering commitment to delivering high-quality results. We're proud to have Climax Technologies on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the GoToWebinar session, dial 877-582-7011. All participants will be in a listen-only mode during the presentation. Feel free to submit questions at any time using the Q&A window located in the upper right corner of your screen. Click the question mark button to open the Q&A window, type your question in the box at the bottom, and click the send button. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is ASM's flagship technical magazine. It provides information about leading-edge developments and trends in engineering materials and the methods used to select, process, fabricate, test, and characterize them. The magazine also covers emerging technologies such as nanotechnology and additive manufacturing, as well as management topics of interest to scientists and engineers. With that, I'd like to introduce the instructor of today's webinar, Marc Lavallee. Marc Lavallee has a metallurgical degree from Trois-Rivières, Quebec, Canada. He worked as a metallurgist in both an aluminum foundry and a cast iron foundry. He also worked at Buehler for 13 years as a sales engineer for sample preparation equipment. Marc has been at Climax since 1997 as a business development manager, initially distributing sample preparation equipment in Canada. His sales involved not only sample preparation equipment, but also method development for his customers. Eventually, his sales role became focused on image analysis products and Climax core products with a worldwide reach. Marc has developed deep knowledge in image analysis at Climax for multiple industrial applications over his 23 years with the company. He has worked in various fields of interest, including metallurgy for applications like grain size, layer thickness, and inclusion rating, aerospace, automotive, and medical devices for cleanliness applications, pharmaceutical applications on particle size, as well as electronic applications. It is a pleasure for me to introduce Marc.
Well, thank you very much, Joanne. Thank you very much for the very nice presentation, and thank you, ASM, for allowing us to present on your network. And I want to thank everybody to joining us during this webinar. So let's get in the heat of the subject because we have half an hour and there's quite a few slides. So what I would like to point out is that the purpose of the webinar is to look at the various methods of capturing coatings and layers. The focus will not be on the nature of the coatings themselves, but how image analysis can address the various challenges of measuring coatings. So a quick overview, we'll look at Climax history, some examples, some various type of coating, what is a coating, basically, and the challenge of measuring the coatings. We'll look at manual measurement versus automatic as well, and some other things. So Climax was founded 30 years ago. I've been part of it for quite a while now. And they developed Vision PE, which is the main software, the flagship software used by Climax. And this is what the software that we used for the coatings that we measured. And one of the strong strength of Climax is that we integrate in-house all the hardware like stage, microscope, cameras to if someone needs something fully automatic. So we're specialists in image quantification, basically. Here's some examples of materials that we can address, as it was Joanne presented in the introduction. So aluminum, so I'll put this little inclusion rating, some very thick carbides, structure, color analysis for aluminum, some non-metallic products like foam or polymers. I'm showing cottons here, but this is an old TV screen here, but we're looking at objects within an object. And some life science, like particle size that we talked about, but it could be fluorescence. Mainly, we're mainly in material, but we can address pretty much everything. An image is an image. Here's an automatic system, while a regular system, that all the components have been integrated. So we control the stage, the camera, the microscope, so the turret would turn automatically, the light would be controlled so that we can recall a parameter that will be set, or an assemble of parameters that would be used for specific analysis. So if someone used a microscope in the lab and then change all the parameters, when you would use it, it would just come back to the original settings. And we can work with various microscopes. So we have a Nikon and Leica. We can work with Olympus, and we can import images for pretty much anything. So we'll see some of that. Yeah. All right. What is a coating? So the coating is basically what it says here. So I'm just trying to move this. A coating is a covering that is applied to a surface. So a coating applied to a surface and called a substrate. So in the middle, quite often we have a bond coat. So if we have a paint, there will be a first layer just to make sure that the top coat will stick to it. So it's the same idea with the plasma or metallic coating. Here we have another example of an industrial type of coating where we have a steel substrate, and all of these layers are there to have a good finish or protection against something. Like it could be heat, it could be sun, it could be scratches. All of these coatings have their own applications. Sorry, I have a bit of challenge changing my slides. Since this is my former life, I want to give a bit of an overview of how to prepare a sample. I know that there are many companies doing this, but just to give you an overview. So when you're working with a coating, what you want is to make sure that you will cut toward the coating first and end with the substrate. So, and also you want to make sure that it will be straight. So if it's at an angle, you will shift your or bias your thickness measurement because it will be larger. So it needs to be straight. And so there are various type of coatings. So there are various methods of cutting them. So most of the time for a ceramic coating, if it's thick enough, a diamond will be used because there will be the ceramic will be cut better with diamond. And then if you have something that is metallic type of coatings, you can use a regular cutoff wheel that is generally made for the substrate. And especially if you have a tough substrate and a thin layer, it's better to use a cutoff wheel all the way, because let's say if you have an austenitic steel and you try to cut it with a diamond wheel, it's not going to work very well. So you need to work with a cutoff wheel that will work for very hard material. And it helps sometimes to mount the sample before cutting it. Sometimes some mounts are too fragile, and mounting them first and then cutting them afterward will help protect them. So you could use a mounting press. Mounting press will be for non-brittle coatings. So if you put a ceramic in there, there's a chance that the pressure will crack the coating. So normally for ceramics, you would use cold mount. And so you could use cold mount epoxy with a vacuum chamber. It's more efficient in the sense that you create a vacuum and then let the epoxy in, and then it will wet in the holes, and then you let the air in, and then, you know, everything will be filled up for the porosity, of course. Sometimes a dye is used also to enhance the porosity. So if you put a green dye or a blue dye or something like that, when you will polish it, the porosity will have the dye in there, so it'll be easier to find them. In aerospace industry, I've seen a lot of people using hard acrylic with a pressure device instead of a vacuum chamber. So basically, it's a 3-part acrylic, and it's quite hard. It's harder than epoxy. And then the way it works is that you put that into that chamber, and then it's a positive pressure, so it's applying everything to the acrylic against the coating, and then it protects the edge quite well. Grinding and polishing, it's important to, it's more efficient, much better to work with an automatic polisher, because it will help preventing mating faces, so that you will have a straighter coating or a more perpendicular coating. So when you put it on the system, you won't have any angle, or it will be minimized anyway. Normally, there's no etching required like you would do for grain size, but sometimes if you have a coating that is sensitive to a certain etch and it's the same color as the one that you want to measure, you could use the etchant to darken the one of the coatings versus the other one, and then it will be easier to measure. Now you will see that we have various tools that help on this aspect. I remember using aluminum foil on some of the samples to make a white barrier on the edge of the sample exactly for the same purpose. The challenge when we're measuring coatings are kind of listed here, but we're not going to go through them because we'll see them in the images. But basically noise, contrast, focus layer, colored coatings, curved layers, large surface. So we'll see that in the next slides. All right, so this is the first coating, which is pretty straightforward coating. What I want to point out here is that the color that we use are what we're measuring. So basically, a basic color, the bit planes are called bit planes. So each of the colors are used to identify or assign to a certain gray level. Now, for example, if I have the ceramic here, it shows yellow, but it could be blue, orange, or whatever. It doesn't matter, because it's the coating, the color that we choose, which we will measure afterward. Now, what we need to do here is to use some imaging tools, because we can see that when we're picking up this red line for the bond coat, we can see that the background is also, the substrate is being detected. So we have some scratches and all. So we have some tools that will get rid of these things. And as you can see, we end up with a proper detection of the coating. Here's another example of a challenge. So we're looking at this coating here at fairly high mag, and the issue that we have is this is out of focus here, and also this area here, which is difficult to pick up because it gets into the same merge of this. So we have some, we use a multi-layer grab, so we can see that all the layers are pretty much in focus here now. So everything is easier to measure. So a multi-layer is basically stacking images. So you go down, capture images as you go up, and it will build up the whole thing. So we're using a gray operation here to detect the edges. It's an edge finder. And so we end up with a proper detection. So if we detect correctly, we have a good measurement. Another example here, we have a coating that is very similar in gray level. I mean, it's some kind of gray, but there's a little difference. We can see that we have a texture here that is kind of smoother than here where we have the porosity and the texture. So we do an operation, gray operation called opening, and then we can enhance those two layers differently because of their original texture. So when we will threshold, so we see only the final result here, but this would be, the ceramic would be red, the silicon carbide would be blue, and the white layer would be all green. So we can see that we can detect them properly, as we can see here in this magnified image. Another type of coating, and this time is from an imported image from an SCM. So SCM are very useful. They give you a certain contrast that are not always available with an optical microscope. However, things like when we have a bakelite here, for example, and it's very difficult to see the difference between the bakelite and the porosity that we have here, which we intend to measure. So in this case here, we're using other gray operation, and then to delimit the lower line, and so we end up with the proper detection, and then we can do an area percent of the blue versus the light blue. The light blue is, we can see here, is kind of a greenish. That means that all the colors are merged. So when we measure the blue versus the background, so the blue is included in the whole coating itself. And then we measure an area percent of the blue versus the light blue. Here, that's not really a coating, but it's still a layer that we need to measure. So this one is segregation in aluminum. So basically, when you're let an aluminum casting, a big casting, to cool off, what happened is that there's the chemistry kind of float. Sometimes you might have some alloys that would float more, and so you end up with some a different structure on the top. Now we have, of course, we have the black here that is one side, but the other side here, the bottom, is not defined. But as you can see here, we can pick them up using a gray operation. It's a top hat that we use for this in this case, and then we can pick up the coatings properly. Color coding, that's certainly one of the challenge. Now in this case here, because the coatings are fairly intense, so if we look at it in gray, we can still detect them correctly. But you'll see in the next one, we have a color that is definitely quite weaker. And if we use a regular threshold, this is what we get. We end up with this background being detected. So it doesn't work very well. So by using a color threshold, basically you click on the yellow here until it's full, and then you end up with the proper detection of our coating. And here's an example, the result at the end. So we can see that the like the greenish line here, the darker green, are here, and then it's following the curve of the coating, and we have our green coating, that is our bond coat, and we have the results. So we have a minimum, maximum standard deviation for the top coating, the bottom coating, and also we have a, I'm not sure if you're seeing this or not, but red porosity versus top coating. So we have detected the whole coating, the ceramic coating, and then we can measure the porosity area percent versus the whole thing. I would like to point out here that we can also pick up some contaminants. Like in this case here, it was a contamination from the bond coat that was like chipped, but it's not really part of the coating. So I want to point out that we can isolate contamination in the coatings. Sorry. Right, so we have another coating here where we have a different challenge. So we have a color that is a coating that has the same color, top and bottom, but we need to measure both. So we have a line here that is also the very similar color. So we can use an edge finder to detect the line and separate the coatings from each other, and then measure the line separately. Curved coatings are certainly a challenge in general, because when you look at this, normally it's straight lines. Either it's going to be horizontal or vertical, but it will be or left to right and up and down. So it's easier to make those lines. But we have this utility that you can make the measurement that are perpendicular to the coating layer. As you can see, it is going from from 10 o'clock to 2 o'clock, right? So, and the angle is keeping up with it. Now here's it's not really a coating, but in this case, it would be behave like the same principle in a sense that the intent was to measure the valley's thickness versus the spike thickness, the teeth rather. And so the idea was to use a tool that we called a radial grid. So basically it makes like a star if you want. And then you pick up all the lines, and then you separate the lines that are part of the valleys versus the lines that are part of the tooth. And then you can get a distribution value for both of them. This line here is, the green lines here are showing that this is cholesterol in a stent, in an artery. And of course, nobody has this issue, but if it ever happens, you know that the thickness of the cholesterol can be measured. So what's important here is that you can see that we can isolate that the longest line, or the longest, the thicker material versus the thinner material. So it gives an idea of a better measurement of the situation for a patient. Manual measurement versus automatic. It's pretty common that in the industry that people will just take a mouse and make a measurement, thinking that, oh, it's quicker and I have an ID. So if you compare with an automatic measurement, instead of having 3 here, we have a good distribution. So if we go back, if we look at the thickness here, so the thickness was measured and picked up randomly to say, well, I think this is my thickest area, and we say 492. So if we look at this here in the green, so we now have a detection throughout, and we have quite a different perspective, because we have a thinner, thicker area. So we end up with a good distribution. And same thing for the lower layer. So we can measure the top and the bottom differently, measure the whole thing, compare. So we can have various comparison possible. And also the main thing is that when someone is measuring automatically, there's no bias. You just get a result. Well, with this manual, someone will choose, well, it's not a good image, it will move somewhere else, and we'll choose the measurement and to the area to measure. It's not necessarily the best information you can get. Here's a multiple task we can do with just in one analysis. By the way, all of those analysis that we've talked about, it takes about like 2-3 seconds, sometimes just 1. So when you're making a measurement, you put your sample on it, you're in focus, click measure, takes 1 second, you have a measurement on all of these grids. So this one here is an aluminum sample in which we the white lines here are clad. So basically a pure aluminum that is deposit or placed over the regular aluminum strip. And the idea is that it would go into a radiator, and the clad is there to prevent the slow the corrosion. So what we need to do is first we need to identify those middle lines. So there's not just one sample, but all of those are separate lines. So again, with those edge finder, we can detect those. And here are our 3 layers that are complete. And then we can see that we can measure the top and the bottom layer for each of the pink. So we have a value here. So we have 3 counts. And then we have a distribution in percentage, area percent in this case, of each layer versus the whole strip. And then we go here, and then we can also do the thickness measurement of all the layers. So we can see that all the layers are measured individually. And so we can have a result that we need. This is what was required at the time for this customer. Here we have another one, which is basically something that is done in the aerospace industry, where they need to measure remaining sandblast particles that would have been embedded into the sample. So when all of these here has to be, there's a certain ratio of length of those particles versus the whole length of the coating. So there was 2 images that were stitched together because it needed to be a certain length. And so we end up with this measurement here where we have the line versus the line of the artifacts or the inclusions, if I guess. And then the line of the inclusion versus the whole line is what is used as a the final measurement. Here we have a another application where we can work with a very large area. So we have this big sample. It's like the amount is about an inch and a half, and then so we generate the coatings, a mosaic of the whole part using a pattern like this. And then it goes to the next one. So once we have acquired this, we can detect the edges. So this is the red line. And then we go here and then we generate some dots. So we have a tool that will generate pattern position. So each of these green dots here will be measured by the system. So in this case, it could be a bit overwhelming that there's so many, just to show that we can detect the whole area, not the area, but all the layers of the coatings everywhere around it. And but they could be spread out. Now the turret turns at 500x from the 50x original, and then the pattern is created. So this is this pattern here. So all of those are dots that will be scanned at 500x. And then we have our coatings here. So the coat, it's looking at it, and then each point of the ceramic layer will be measured all around. So you can have the perfect description of your component. Now, this doesn't take that long also. So when you put the sample, you click go and you walk away, and all of these operations will be done unattended. So at the end, someone can go back and validate the results. So when I talk about validation, we're talking about this, like this is here a decarb layer. Now, so again, it's not a coating, but it's still a layer to measure. Sorry. So we measure all the layers, and we have this like Excel-like sheet that we have called the data browser. So when you double click on it, it will show the actual line. So if you have something that is out of spec, you can check it out. And if it is an artifact that somehow it could not be removed, you can delete that, and then it update the data accordingly. So it's very powerful tool. So the stage move, and it moved to that specific points. Regarding calibration, we have this tool that is very useful to especially if you get audited. So this one will allow an automatic calibration. So basically, it will detect the serial number. That it's not this one here, but it's inside that little rectangle. There's a barcode, and it will detect the serial number and apply the calibration of the serial number to the area that you're measuring, as it was originally defined during the certification. So it's quite useful. And you have a NIST certificate along with it. So in conclusion, the softwares work with most of sample type. We haven't seen area that it doesn't work. If it's well prepared, it should work. There's quite a few methods to achieve the measurements. And I've noticed that the manual measurement can be quite less efficient than the automatic measurements. And we have various threshold methods. And also I want to reemphasize the fact that we can control motorized microscope to make something fully automatic so that all the analysis will be done the same way. And we can address all kinds of metallurgical application. So thank you very much. And I would like to ask Joanne to take over for the Q&A session.
Thank you, Mark, for that excellent presentation. I think we only have time maybe for just one or two questions.
Yeah, sorry.
So one question is, can the multi-layer grab be used with a manual microscope?
Yeah, you can. We have a function there that the multi-layer grab is basically, normally you use a motor to stack your images, but you can also use the focus. Either if you're working with a stereo, there's a little extra tool that you have to put in there, but you could use the multi-layer grab on a manual microscope or motorized microscope. So you don't need a motorized stage. It's just better with a motorized stage. So a manual microscope can work with stacking or, yeah.
Okay, good. I'll ask one more question. Can I import images in the Vision PE software coming from another microscope with an existing camera?
Yes, you can. Actually, it happens fairly frequently. So ideally, let's go back to the microscope. So if you have another system and you have the software, you can import images, and the software will ask you to calibrate it before you make a measurement. So normally, if you save it with a micron bar on it or some kind of a reference, you can recalibrate the image like we did for the SEM image that we had earlier. But it's better if you could acquire directly from the camera, because we have, you can do stacking, for example, and also we have a shading corrector that evens out the image, the illumination. So it's better to acquire from a complete system than from the outside, but it's possible.
Okay, thank you, Mark. Unfortunately, we don't have time to answer all of the questions we received, but in a few days, all participants will receive an email with further contact information. I encourage you to complete the brief survey that will appear on your screen as you exit the webinar. With your input, we can continue to provide webinars with high quality, practical information that you can use. I also encourage you to follow up with Mark for more information about coding image analysis. Once again, I'd like to acknowledge the sponsor of today's webinar, Climax Technologies. With their unwavering commitment to delivering high-quality results, Climax Technologies builds tailor-made solutions that best suits their clients' needs. For more information, visit climax.com. Thank you again for participating in this ASM webinar. Have a great day, everybody.